Welcome back to our 12th chapter series of lectures on water management, the Israeli experience. We are today at chapter 8. My name is Yoram Orav. I am the Special Envoy for International Water Affairs at Mashav. As some of you already know, Israel, a semi-arid country, has managed in the last decade to solve its acute water challenge. The secret lies in a holistic, integrative approach to the subject. A lot of challenges to confront, and none of them can be neglected. We already spoke about the important role of wash and water management in difficult times, relating, of course, to the corona crisis we are all confronting. Water management in agriculture, education regarding ways to reduce water consumption, water harvesting, disruptive and sustainable water technologies, and urban water loss reduction. The future lectures that will take place every Tuesday at 12 o'clock GMT will discuss water reclamation, desalination, national and urban water management, and last but not least, innovation and water tech. Today, we have the honor to host Mrs. Sara Elhanany, former director of the Water Quality Division, Israel Water Authority. Mrs. Elhanany will talk about water quality preservation and remediation, present and future challenges. But before giving her the floor, a few technicalities with your permission. The lecture is recorded. It will be uploaded to the YouTube channel of Mashav MATC and will be available there together with the recordings of our former lectures. It will also be available now and later on Facebook Live. Look for the page of Mashav MATC. Questions, please write them down here on the chat option, addressed to everyone. Mrs. Elhanany will answer them at the end of the lecture. The lectures are a joint venture of Mashav MATC, our training center, and this is a good time to thank Alina Domcic and Ora Rabin for all the hard work they invest in this program. And Mashav, Israel's international aid agency, please join us for a 100-second clip on Mashav. After that, I promise the lecture. And now I will have to manage with a Zoom, so bear with me for a second, please. First thing went well. Second thing went well. Share, screen, and play.
Mashav, Israel's Agency for International Development Cooperation, was launched 60 years ago to share the know-how and technologies which provided the basis for Israel's own rapid development. Mashav aims to empower those living in poverty in a holistic and innovative way and support fellow nations and communities in their struggle to achieve sustainable development, placing people at the heart of its initiatives. Our agricultural programs use unique techniques and farming methods to increase sustainability, food security, and hunger eradication. We believe that investment in education is an investment in our future and an agent for change around the world. We coordinate Israel's official humanitarian assistance, building medical facilities and supplying medicine in the wake of earthquakes, floods, famine, and other disasters. Mashav promotes innovative entrepreneurship as a means of advancing growth and prosperity. We believe that gender equality and women's empowerment are central to reach sustainable development. Our philosophy is to leave no one behind. During 6 decades, Mashav has trained over 300,000 people from more than 140 countries and has established development projects worldwide. Mashav, Israel's Agency for International Development Cooperation, is celebrating 60 years of sharing its experience and partnering for a better world.
Actually, we're already 62, so you can understand that this clip is 2 years old. Okay, and Sarah, are you with us? The floor is yours.
Hello, everybody, and welcome to my study room in Nes Ziona, Israel. Thank you, Yoram, for inviting me to take part in your important course on water management, and thanks, Elina, for your technical support. As Yoram already mentioned, I have retired 3 years ago from my position at the Israel Water Authority as the director of the Water Quality Division, which we established only on 2002. Today, I teach students at the Hebrew University on water quality improvement, reclamation, and water treatment technologies. I'll focus today in my talk on some water quality issues with some new findings that are becoming recently more and more challenging to cope with. And let's start from space. Now here is how our planet looks from space. It looks blue, because it is covered by water, mainly by water. But 97%, as you know, is salt water in the oceans. Another 2% is fresh water, but they're trapped in glaciers. And only 1% of the total water on Earth is available fresh water and available for our use. That is why we call our world a water-thirsty world, and that is also why our main problem is not water quantity, but water quality. The 1% availability is consistent mainly on groundwater, which are also the more reliable water source. And in Israel, indeed, we rely mainly on groundwater. We have 2 main aquifers, groundwater reservoirs. One is the Western Mountain Aquifer, which contributes around 1/4 of the total potential. And it consists mainly on carbonaceous fractured rock with a very rapid flow to the sea. The coastal plain aquifer consists on calcareous sandstone. It is a porous media aquifer that can also store water from year to year. That's why we call it a multi-year reservoir, and that is why it is the most important one. This aquifer is also underlying the most populated area in Israel. Here is Tel Aviv and suburban, and there are some more big cities in this area with a very intensive industrial, agricultural, and urban activity. In Israel, we have only one fresh lake, which is the Sea of Galilee. It used to be in the past the main water source for our national water carrier. But today, because of climate changes, less precipitation, especially in the northern part of Israel, it contributes only less than 5% to the total supply. The total availability, the total what we call potential production, yearly potential production in Israel comes to only like 1.2 billion cubic meter, 1.2 billion cubic meter. That is the all availability of natural fresh water with some brackish water, mainly in the southern part of Israel. While the consumption is almost twice. Here is the demand, the water consumption in Israel comes to 2.34 billion cubic meter per year. The domestic utilize less than 40%, 38%, then 5% the industry, and we have also nature with that is also a water consumer with a water allocation to maintain the ecosystem. So we pour water to streams. And by the way, all the water in Israel is allocated. So there is a good control on the consumption, on the production. The agriculture consume 55% of the total consumption. In the past, the agriculture used to rely only on fresh water, natural, that came from natural sources. Today, because of severe cuts in allocation in the past, because of water shortage, the agriculture is relying mainly on recycled water, marginal brackish water, but mainly recycled wastewater, which contributes today 62% to the total agricultural consumption. So we have here a deficit of about 50% of the consumption toward the availability. This deficit was causing in the past overexploitation of our natural sources. As we can see here in this example, this is, you can see here the water level in the coastal plain aquifer. Naturally, it was draining from high level in the east to the Mediterranean Sea. It was a nice gradient, allowing the groundwater to wash and to drain to the sea. Today, because of, look what happened here between 1998 to 2005, in this period, Israel was facing many drought here. There is almost 7 years of droughts. And so we overpumped, overexploited the storage, the groundwater storage, creating very deep depressions in the water level. We can see here in red -2, but this depression were down to even -6 below sea level. So it allowed the attraction of seawater, and salinity became here a big problem, a big issue in the coastal plain aquifer. This is the result of overpumping, overexploitation, or exploited groundwater. We can see here one of the results in salinity. The pristine condition on 1934, before developing the aquifer, most of the storage was below the recommended level, which is 250 milligrams per liter. By the way, the drinking water level for drinking, it is 400 milligrams per liter, but the recommended is 250 for drinking and mainly for irrigation. What happened after those over-pumping, over-exploiting the aquifer on 2005, you can see that most of the storage exceed the recommended level of 250. So this is a result in salinity, but it is not only in salinity, because those depression also enable the accumulation of more contaminants from human activity, that naturally were draining to the sea, but today they accumulate in those depression and were not washed out to the sea. So this is an example of how water scarcity leads to overdraft operation and leads to finally to water quality deterioration. Now, this was a well-known, well-recognized phenomena on the beginning of the 2000, and this also led to adapt a new approach, new policy, a more sustainable approach in order to close the gap between the demand and the availability. This policy was consists on those 5 measures. First of all, to reduce water consumption by much more efficient use of water in agriculture and also domestic. This was done by using technologies and also new regulations. And this was also the more cost-effective measure. Then the reuse of wastewater effluent for irrigation by increasing the capacity of wastewater treatment plant and also upgrading effluent quality, which you must do if you want to replace fresh water by wastewater. And then we had no choice but to go to manufacture more water, from sea by desalination of seawater, but also brackish water, and adding not only quantity, but also improve the water quality. And last but not least, to improve water quality by remediation of those contaminated area in the aquifer and by treating the domestic drinking water wellhead treatment. Now these measures also introduce new type of water to our system, mixing different types of water with different chemical composition, like desalinated water, groundwater, surface water, and wastewater. Now, mixing of different types of water can cause a reaction between one type to another. For example, desalinated water, when they meet with desalinated water, has low buffer capacity because they have no mineral. So when they meet, for example, groundwater with low pH, they can lose their chemical stability and be corrosive. They can corrode the metal piping, releasing ferric oxides. This phenomena was, we experienced this phenomena, we call it the red water phenomena. This was caused by the mixing of desalinated water with groundwater. But they don't have to mix with each other. One source can also impact other, just by, for example, the desalinated water can affect wastewater, and I'll show it in a moment. So the introducing of new water types to the system requires, no doubt, a more integrative, holistic approach in their management in order, first of all, to avoid adverse impacts, but also to see how we can benefit from one source to another, and this is feasible, as I'm going to show you now. By now, I'm sure that most of you know that Israel has a world record in recycle wastewater. We reuse the 85% for agriculture. Of the 85% of the treated wastewater, we reuse it for irrigation. And Singapore is also recycling water, 35%, and Australia, USA, China, Spain, they utilize only less than 15%, but most of the world do not recycle wastewater. Wastewater are disposed to the environment in most of the world, and polluting, of course, also water sources. In Israel, wastewater, treated wastewater became a very important source for agriculture, as we can see here. Before, only like 20-25 years ago, the agriculture in Israel was relying on fresh water, potable water. Since 25 years ago, we started to use more and more effluents. Today, 62% of the total water for agriculture comes from recycled water, mainly wastewater, but also some brackish water. And this trend is increasing. Hopefully, we'll reach the 90% of recycled wastewater for irrigation. Now, no doubt that using the wastewater has many benefits. Not only saving natural water resources, but also recycled wastewater creates a sustainable platform for future agriculture that was in the past subjected to cuts in allocation. Today, they have first of all, a much cheaper source of water in comparing the alternative of desalinated seawater. And of course, it also prevents water resources pollution. But replacing fresh water by recycled water also puts some responsibility, very severe responsibility on the government to ensure that the users will not be affected, will not be damaged by using wastewater. So this is the reason why on 2010 we issued the new regulation, effluent quality standards, in order to protect public health, to prevent contamination of water sources, to protect soil, agriculture crops, the farmers, and also to protect the environment. The regulation consists of 38 parameters. Here are some of the main parameters. Chlorides, sodium, and boron are the most significant parameters for the farmers, for agriculture, in order to not to damage the crops and the soil. Chloride must not exceed the 250, the recommended level. This is a standard, and sodium 150, and the boron 0.4. There is a direct correlation between salinity and productivity, and indirect, of course. As salinity increases, the yield falls. As we can see here, above this threshold level, it differs from one crop to another according to the sensitivity of each crop. Here we can see strawberry are the most vulnerable. Above this threshold level, for each unit of conductivity, we can see a decrease in productivity, in yield. For strawberry, it will be for each one additional conductivity unit, it will be a 33% of decrease in productivity. In oranges, it will be 16, tomatoes almost 10, and wheat and so 7, and so on. Now, we must understand that salinity cannot be removed, chloride, sodium cannot be removed, even boron, during the treatment process of wastewater. It must be removed at the source. There are two ways to control salinity. One is to remove it at the source by using in the household less saline products, and the industry to use also less salinity, or to remove it before connecting it to the wastewater treatment plant. And this was done by regulation very successfully in Israel in the past, but this is not enough, because the household contributes about 100 milligram, the regular use of chloride, to the sewage system. So we have to control the source, the background, the supply water, if we want to control salinity. And this is what happened in Israel. We can see here before 2007, these are the chloride concentration in the central parts of Israel, where most of the wastewater are treated and being reclaimed. So it was around 290, almost 300, so it is above the recommended level. And the farmers on this time were not so satisfied to get wastewater, because they experienced in some places a decrease in yield. And this happened if you supply water with 200 milligram chlorides, then you get in the wastewater about 300. Since then, we can see a nice decrease in salinity, and now it is less than 200, so we succeed to decrease the salinity by more than 100 milligram per liter. And how it happens, I'm sure that you can guess. This was by desalination, adding desalinated water to the system. We are desalinating seawater since 2005. Today, we desalinate about 600 million cubic meter. So we can see here a very nice correlation between the decrease in salinity and the annual production of the desalination plants, pumping to the, adding to the supply system. So this is example, a good example, as I promised you, to see how we can benefit from one source to another if we control it. And let's see what is about desalination. So as mentioned, since 2005, we started to desalinate seawater, and today we have 5 large-scale desalinated plants along the seashore. They are all connected to an existing infrastructure, and this is very important, to the national water carrier. There is a new one, Sorek, that is going to be constructed and supply water in a couple of years. Today it's in the last stage of the tender procedure. And this will be the biggest, the largest one of its kind in the world. So today, around 600 million cubic meter are desalinated water that are about 1/3 of the total supply in Israel and 70% of the domestic supply. Now, this Now, let's see what about the quality. I put here together some water quality requirements from the desalination plants in Israel, comparing the one of the biggest desalination plant in California in USA, in Carlsbad, which was constructed 4 years ago. Let's see what are the demands, the requirements in Israel. For chloride, for example, it is 20 milligrams per liter, while in the United States, in Carlsbad, it is 150. And so I'm sure you understand why we are going with such a low level of chloride, because most of the water in Israel are recycled, and if we want to impact wastewater and to prevent groundwater salinity, as we saw, it is an issue on the Coastal Plain aquifer, but not only. So we have to go down by chloride, and then also boron. In the United States, it is one. One is the drinking water level, the drinking water standards in Israel and in the States too, but we are going lower than that because crops are much more vulnerable than a human being to boron. Boron is toxic in high levels for some plants. So the total dissolved solids in Israel, the requirement is 300, while in the United States it is twice. So you're probably asking yourself, now what is the price for it? For example, for boron, we have to go for one more stage in order to remove boron. And it is, of course, it costs. And so let's see what do we have to pay in order to get better water quality. Now, here is the answer. We are not paying more. On the contrary, Israel is still the cheapest in desalinating water. Here are the three large desalination plants in Israel: Sorek, Hadera, and Ashkelon. It is about 50 cents, 50 to 55 cents for those desalination plants. While in Carlsbad, that we already met, it is 3 times more than in Israel. By the way, it is the same company that constructed those all those plants. It is the IDE, an Israeli company. Now, what is the reason? There are 2 reasons for the low price in Israel. First of all, as we already noticed, all the plants are connected to an existing infrastructure, to the national water carrier, and this, of course, is much more convenient and very effective. And the second reason is the type of tender in Israel. It is a BOT, Build, Operate, Transfer, or PPP, private-public partnership with an effective risk allocation between the private contractor and the client, which is the State of Israel. Now, to conclude this part of my talk, I want you to notice that only 70 years ago, Israel was relying mainly on natural water resources, and we saw what happened when we overexploited those natural water to meet the demand. And today, 50% of the water is manufactured water by seawater desalination and also by treating wastewater, recycling wastewater. This water evolution, what we call from survival to sustainability, is based on technological, economical, and some also administration capabilities. And today we can say that we overcome the water crisis in Israel. But and something else that I want to mention, that natural water resources will not be replaced totally by manufactured water or by we always will use natural water resources, and it will be one of the most imported water resources. And this is because, especially in our region, natural water resources, the essential strategic asset, but it is also a sustainable resource for a future generation. We must keep it for a future generation, and this is why preserving natural water resources and improving water quality became the main challenge in water management in Israel, and but not only in Israel, all over the world. Now let's see what happens here. We were talking about water quantity. Now we are talking about more about water quality. In the last 20 years, 20% of the drinking water wells were closed because of contamination. 50% were closed because of nitrates from agricultural origin, mainly not necessarily wastewater. It was even before we recycled the wastewater, but because of natural reason, by oxidizing the cultivation of the soil, release nitrogen only by exposing it to air, to oxygen, releasing natural organic in soil contents. So this nitrous phenomena we can treat. We can also dilute, mix water, but we are much more concerned today because of those contaminants that I marked in yellow. These are all contaminants that are from industrial sources. They are much more risky in very low levels, in the range of part per billion or even part per trillion PPT, like organic pollutants, volatile organic compounds, chlorinated solvents, EDB, which we use in agriculture for sterilizing soil and as a pesticide, and also some fuel additive. Some of them are not even regulated, but those contaminants in very low level can be very toxic and even carcinogenic. We started to detect them recently only because the analytical capabilities were upgrading, so we can now detect them in very low levels. Now, the problem is not only closing drinking water well. When a well exceeds in Israel the drinking water level, we close it. We can treat it then to remove the pollutants and connect it back to the supply. But this doesn't solve the problem. The problem is the contamination in the source, in groundwater, that expand in groundwater and is spreading out and contaminate more and more volume of water. In order to stop it or to treat it, we have to detect it first, and this is not an easy task. Let's see how we do it. This is a GIS mapping. You can see here the layer of the production wells. In green and pink are the radius of influence, and we can see above the, for example, the fuel pipes and the gas station here, and then we can see the industrial areas. All above, this is another layer, and then the irrigating areas by wastewater with the wastewater treatment plant and the reservoir, and then we have all the big cities of Tel Aviv, Ramat HaSharon, Herzliya above the drinking water, above the replenishment area of the aquifer. Now this is the base for planning a good monitoring network, and the idea is to put a monitoring well between the pollution site, a potential pollutant site, and between the drinking water well. And today the monitoring network consists in this area of 1,500 monitoring wells that are being drilled between the domestic, the drinking water wells, and this is one of the industries, for example. Now this is not enough. We need to have also an analytical supporting tool, and this is the National Water Laboratory, which we established together with the Water Quality Division in 2008. And the aim of this laboratory, that it is one of its kind in Israel, with a very diverse capability to detect many, a large variety of contaminants. That's why it is unique in Israel, and we succeed to develop new analytical methods for also for unregulated contaminants, like that are not yet in the drinking water standards, but we have to detect them as well, like industrial complex, explosive, pharmaceutical, personal care products, and this was done in the last 20 years in this laboratory, and it enables us to detect many new contaminants in our water resources, together with the monitoring network. And we can see here the outcome. This is the outcome of the analytical efforts. We detect here about 4 big contamination plumes in groundwater. The red are contamination plumes in groundwater. And I want to emphasize something. The foundings are new, relatively new, 10, 20 years, but most of those contaminants were, and this is very important to remember, were there even tens of years before we detect them. So you will not know if contaminants are there, even in your drinking water source, if you will not detect or monitor them. The main contaminants that those plumes are contains are volatile organic compounds, which are like chlorinated solvent, trichloroethylene, tetrachloroethylene, which are very common in most of the industries. And then we have also some fuel additives. I'll talk perchlorate, I'll mention it later. The total volume, by the way, is huge volume, 2.3 billion cubic meter, which comes to all the consumption in Israel, which is also the 10% of the total groundwater storage in this aquifer. I am going to zoom into one of the plumes just to show you what are the findings and how we treat them. Today, we put a lot of efforts to treat those contamination plumes. Now, this is one of the largest one in Israel that was first to be detected of volatile organic compounds from industrial source. It is a huge plume, like this is Tel Aviv. It is about 16 kilometers on 3-4 kilometers here. The colors are according to the intensity of the contamination. The most contaminated area is the red one here in the center, and then we go to orange and the yellow. Most of the contaminants here are chlorinated solvents, as I mentioned, which are also very toxic, and some of them are carcinogenic in very low level of part per billion. And the risk for human is not only by drinking water. Of course, if you drink water with high level, it is risky, but also by breathing, by vapor intrusion to buildings. And this is another issue of those contaminants. They have a large range of uses. In most of the industries use those chlorinated solvents. It doesn't have to be a big industry. It can be just even a small garage, small dry cleaning, paint remover, solvents used by degreasing as degreasing agents, and so on. And even in the past, they were used for the producing the decaffeinated. For example, Nestle used them as to extract caffeine. So many sources. The remediation methods to cope with those contaminants, to treat and to remediate, divided into two. We have two strategies. One for hotspots, or what we call for a source zone. If you have a source zone, you can treat it by in situ remediation, by injecting a solution that can decompose or biodegrade the contaminants. We can use chemical oxidation or chemical reduction or biological treatment according to the pollutants. But if you have an extensive plume, as I'm going to show you in a moment, we cannot in situ remediate, we cannot remove all the pollutants, but we can control the plume. And we are doing more of controlling. We can do it by hydraulic containment of the plume to prevent it expansion. I'll show only one example of each strategy. This is by in situ remediation of hotspots that is located here in the southern part of this huge plume in the industrial area of Hulon. Plume in groundwater 600 times higher than the maximum level for drinking water. Drinking water is 20, and this is, here we found 12,500. This is a very high concentration in groundwater, so we have to treat it before it will expand more and more, because it already caused the pollution of some domestic wells that were in the neighborhood. Now we choose here the chemical oxidation because of the type of the pollutant and also the condition in the area, using permanganate, potassium permanganate as a salt, but permanganate is the oxidizer that can oxidize, for example, trichloroethylene. This is found here in high levels. It breaks the double bonding of the molecules, and only after 6 months, we can see the area is clean. It was chemically oxidized to non-harmful compounds. Now, this is one example. The other one is, I promised you, a huge plume. This huge plume is located also in one of the most populated area, north to Tel Aviv, in Ramat HaSharon, underlying military industry that used to, it was active here more than 70 years. And the plume consists on not only one pollutant, but we have, they use the they have many industries, they are small industries, they use many chemicals, and I must emphasize that they are not, they were doing very good things to they develop the industry here, but those days, there were no standards, environmental standards, and they didn't even know the impact of those contamination. For example, of the perchlorate, it used to be disposed to soil here and also in the United States and everywhere, because people were not aware of the risk of this contamination. Today it is controlled, but this was creating a huge plume, especially the perchlorate is created the largest plume. This is the plume of the perchlorate. Now, what is perchlorate? Perchlorate is ammonium perchlorate is salt. There are many used for solid rocket fuel, solid rocket fuel. That is very highly soluble, and when released to groundwater, it spreads out and it can create a huge plume. It is not carcinogenic, but it inhibits the thyroid gland function, the metabolism that is regulating the metabolism of adults, but also regulating children development, so it can interfere with children development. Perchlorate was found in the United States, in many states, in 15 states, and affected the more than 100 potable water system. It was related to the activity of NASA, as they use it, as I mentioned, for solid rocket propellants. As a solid fuel for propellant, for rocket propellant, and it was found there on late 90s, as in Israel found it 20 years ago. So this is the plume of volume of 650 billion cubic meter, which is a huge plume, area of 25 square kilometer. And as I mentioned, perchlorate has no standard, drinking water standards, not in Israel, nor in the United States. It is not regulated yet, but the recommended level is by the EPA is 15 part per billion, 15 micrograms per liter, and the concentration that was detected here under this industry that they were producing the perchlorate here, manufacturing it, and disposing it to ponds, to infiltration ponds. The concentration here in groundwater was very high, 850,000 ppbs, and this is the recommended level, and it causes the, when we detected here, we went to detect all the domestic well of those cities of Ramat HaSharon, Herzliya, and Tel Aviv, and they all were affected by perchlorate. We had to close them and to bring alternative water to Ramat HaSharon. The remediation strategy, as I mentioned, cannot be we cannot remove everything, we cannot do it in situ, but we can control the plume in order to get it shrinking. And it is done by 6 wells This was, of course, was based on a modeling effort, on a model to many simulation to choose the optimal strategy, and pumping here around 600 cubic meter per hour, 6 wells, in order to change the gradient. Instead of flowing out, the water, the gradient will be toward the contaminated area, and will pump the water and treat them. So to remove more of the contaminated to pump in at the source, and to remove most of the pollutants by treating them. We can see here the simulation. These are the wells. After 20-25 years, they are, the concentration went down to almost 0, and the plume is shrinking. Most of the pollutants are out. And we can see here a nice simulation that was done by Dr. Michael Rona from the Water Quality Division, simulating the what happened after 20-25 years, the shrinking of the plume, removing 2,000 tons of perchlorate, so most of the perchlorate will remove. But it is not enough. We have to treat it. We cannot just dispose it. You cannot use it for agriculture because it will accumulate in plants. So we have to treat it. For this reason, it was constructed here a demonstration pilot plant and this was constructed, by the way, by a joint venture of Israeli company, Shikunu Binui, with Envirogen, which is the American companies that brought the knowledge. And this pilot plant, demonstration pilot plant, was running for 1 year, successfully removing all the pollutants. The aim of this plant was to examine, first of all, if this is feasible from a technical point, and second, what will be the price for a full scale plant if we want to treat it, to treat all the plume. As mentioned, it was a very successful treatment plan. We succeeded to this. These are the levels that were pumped from a monitoring from a small well here, and this is the output. The treatment was based on biodegradation, biological treatment using bacteria that can utilize the oxygen of those contaminants of perchlorate and also of nitrate, and degrade them, biodegrade them. And then there are also more filters, more technologies to treat all the contaminants, even the heavy metals, chromium. Now, this is going to, of course, to upscaling and hopefully to remediate this area, which will enable the development of the area for residential and building more than 23,000 housing units. Now, I was talking about how we treat water in the sources, in groundwater, but we also treat, we wellhead, treating the domestic wells by many technologies. Some of them are Israeli development, like Atlantium, the AUP-UV, like here we have nitrate removal. We don't have time to go into all the technologies, but most of the wells that I was mentioning, the table that I showed you, most of them are being treated by one of those technology, and this is also supported by the government, by levy exemption. I want to show, if I have time, For one more example of nitrates caused the closure of 10% of the drinking water well in Israel, and this is the northern part is a very we use there a lot of irrigation. It is agricultural, used to be agricultural area, and today we treat, we remove nitrates from groundwater by mainly two methods. Reverse osmotic and also selective electrodialysis. They are both membrane treatment. The problem is that they leave brines. This is what happens with membranal technology. Recently, we started with a new approach. It is not only in Israel, in all the world. The trend is to go to a biological treatment, which are much more green environmental technologies, because they degrade most of the pollutants, leaving no brines. And here is one example of this is a development of Israeli company, Equise. They developed this carrier. The idea is to biodegrade nitrates for drinking water purposes by the nitrification process. Bacteria can utilize, as I mentioned, the oxygen of the nitrate and degrade it to non-harmful compounds, and this is done, this carrier can carry on the biomass, the bacteria, with a large surface area, and this is used in those bioreactors. We'll not go into details, we don't have time for this, but after treating it, after filtrating and chlorination, we can safely use those water for domestic well, and this is the first well in Israel. This was supported by the Israel Water Authority. This well is now treating nitrates by this biodegradation technology of Equise, and the advantage is that it has no brine, it is a green process, full biodegradation, and a small footprint, and also the price is not higher than the membranal technologies. So I just want to mention also for wastewater treatment technology, we are developing in Israel those technologies also for treating wastewater, which is very important. This is a company that is using algae as an oxygen source to for the treatment process. Normally we enter oxygen by aeration, but this is energy cost. Now here they use algae for that can convert carbon dioxide to oxygen, and reducing the price of energy, which are normally very high. The company is called Aquanos, and they have they use it here for very high organic load wastewater, like dairy farms. They use it in Israel and all over the world. And we can see here, this is a delegation that was here 2 years ago or 3 years ago. This was still in the pilot plant stage. Now it is commercial technology, a successful one that is used all over the world. And just a few conclusion marks. We saw that Israel was successfully managed to cope with the water shortage, and our next challenge is to preserve our natural water sources that are a very important asset in Israel, not only a strategic asset, but also it is very important resource that we want to leave for future generation. And we are doing it now by developing this monitoring system to detect, to stop the pollution, to remediate, to protect the drinking water source. And I have to mention that today drinking water wells in Israel are of very high quality, and it is very safe everywhere. You can everywhere drink water in Israel, and this is also for the reason for it is also the protecting those wells by this monitoring system, and the pollution plumes and source zone remedial action were successfully implemented. First of all, due to their detection. So we put a lot of efforts today to remediate those after detecting them. And last but not least, the preventive measures are much more cost effective than those remediation action. And I cannot, just because you can see it doesn't mean that it doesn't there. And as I mentioned, those VOCs, that became very widely spread in almost everywhere that we are detecting them. They have no smell, they have no taste. You can drink them and becoming sick without even knowing. If you don't detect them, you will never know that they are there. So in other words, as Chezi mentioned before, what is not detected, what is not monitored cannot be controlled. And I cannot finish this talk without mentioning, without acknowledging this unique team that I had the privilege to work with. This is part of the team on this is the laboratory, the national laboratory, and here is the whole team. This is, by the way, the underground pumping station of the national water carriers. So thank you very much.
There was one question regarding bioremediation that I think that you have answered in a sense. So the next and maybe the last question, because of time limits, will be regarding those things that we cannot see but are still there. And there are two concerns, big concerns that are being spoken about during at least the last year, and both of them are dealing with very, very small ingredients. One of them is, and both are dealing with the agricultural use of treated water. One of them is regarding hormones that are left in the sewage from medications, etc. And another problem that was being raised recently was regarding microplastics. That some researchers claim that they find ways to enter, especially green leaves. What can you tell us in brief about that? And do we have the technology to tackle this problem as well? Do we have filters that can filter microplastics, for example?
Yeah, okay. I'll start with the microplastics, because this is really something new that is now very, very in. Microplastic, there is no containers that it really affect. It has adverse effect. The risks are more directed toward the components of the plastic during manufacturing, like phthalates and those, but they are not in the microplastic, in those small pieces, less than a millimeter. Yeah, so, but the microplastic can also be a vector for some contaminants. It can carry on it and can release it. and can release some of the contaminants that are absorbed to. Hormones. Okay, this is my favorite, and this can be another lecture. We are working on those pharmaceutical hormones, PPCs, and what we call endocrine destructive compounds from domestic uses and also from pharmaceuticals. We are working on this issue many years, but I can just say one conclusion. The levels, we can find them in drinking water and groundwater. In the Benny Heffitz works on the agricultural products that are irrigated with effluents. You can find them, no doubt. But you can find them only because you know today to reach very low levels of PPT, part per trillion. So that is why you can detect them today. But it doesn't mean that it is adverse effect and it is risky. Of course, we use them in our research as a tracer. We know because we can go to very low limits, and if we find them, we know that there is a connection with wastewater and there is a leakage somewhere, so we can treat it rather than for health impacts.
We are also invited to join us next week. Next week, as I think we mentioned already, we will host Dr. Tomer Kreitzer, and he will talk from his experience about water treatment and water reclamation. In a sense, it's tied, I think, very well to your lecture, and the guy that thought that this lecture should come before the next lecture has done a very good job. I wonder who he was. It's time to thank you again so much for all the information that you gave. I suppose that you will be more than happy if people will send you emails with other questions. You can do it through Alina here. Alina is going to send everybody, apparently in the beginning of next week, she will send you the link to the lecture. And of course, you will have the presentation over there as well. And you can send back some questions if you have more questions to Sara. And again, I remind you that almost except for one, all the lectures that we had, which means that we have 7 already, are posted in the YouTube channel of Mashav MATC. So in a sense, you will be able to go back to this presentation also through there, and to go back also to our former lectures. So thank you again for your patience and for being here with us, and I hope to see you all next week. And goodbye from Shtaim.
Thank you. Thank you.